Let's talk about the common mode feedback circuits. Let's suppose you have a pull-up and pull-down current and the output impedance RP and RN. Let's say if there's any small mismatch current between IP and IN, the difference will have to flow through the RP and RN in parallel. Because of the high output resistance, typically, if there's any small amount of current flow through the RP in parallel with RN, IP, this is small signal, let's say, in current, then output goes to infinity. It may go to either positive infinity or negative infinity, but practically the voltage is limited by the supply, so either VDD or ground. So the output voltage will stuck to either VDD or ground. So it is important to there's some kind of feedback so that they exactly match this up and IN current. The up-down current must be exactly matched. For example, on the right hand side, telescopic amplifier, if you look at this, you can immediately identify the pull-up current source and pull-down current source. Ideally, this level must be exactly matched to, let's say, ISS over 2 and ISS over 2. But in reality, there is some mismatch, right? What kind of a mismatch can contribute such kind of error? For example, so different VDS, right? Different VDS on the current source, current meter, will generate the current error, right? Even though we flow like a 300 microamp here, from here to there, let's say 10x larger device size, right? W and 10 times the W, but the resultant, the output current level is not equal to 3 milliamp, right? So this is the problem. And also, this drain voltage and the gate voltage, this drain voltage of the M10 and M9 is different, and also M11 drain voltage and 7 and 8 drain voltage are different. So you cannot guarantee that the same current. So the first region is that channel length modulation, those effect, you know that the current meter error coming from channel length modulation, meaning different VDS, different VDS, right? Now second, the VTH variation or mismatch. The device mismatch will result in the current error, right? So that's gonna be, so whenever you have a pull up and pull down current, something like this, you need something to measure and monitor the output voltage level, so that that output level to be desired level. We have to control some kind of a feedback to either control the upper current level or down current level, right? So this kind of a feedback, we have to, there's some kind of feedback CMFB circuit must be there. Let's take a look at the more in detail. So any feedback circuit here, pull down and pull up, and sense the output level, and then find the common model level of the output. So this is kind of a, even though the amplifier swing like happen V out 1 and V out 2, like this, right? The common mode level is defined by what? This level, right? So V out 1 plus V out 2 divided by 2, right? This is V out 2, for example. So since this common mode level, right? This common mode level, this is V out 1 plus V out 2 over 2, right? Sense this common mode level and make that to desired level by having the amplifier, operating amplifier. So OPM there, so we construct some kind of a negative feedback. This is a negative feedback, right? Once the negative feedback happen, let's say why it is negative feedback. For example, if the common mode level, let's say for example, go up, and the output will go up, then the output will go up. The voltage here goes up. Then what? The pull down current increase. The increase in pull down current will move the output level common mode to go down, right? So this is kind of negative feedback. So once the negative feedback strength is high enough, strong enough, then the difference will be 0, right? This is error amplifier. So error amplifier, the role of this OPM is error amp. The input, at input, the voltage V at input is always 0, right? Okay. The most simplest common mode sensing is using the two resistor. So R1 and R2 is the same. Make it large. So how large it should be? So R must be large enough that output ROP, output impedance, amplifier output impedance, let's say R out, right? Because this is a cascade amplifier, the R out is approximately what? GM RO square, right? So this is a quite large output impedance, so you have to make a very large R. So this results in large area and parasitic capacitance to substrate. If you think about the poly resistor layout here, you have a very large poly, right? You have to, for making large resistor, you have to make it like a array of the poly resistor and contact there. And then connect the, you may need to connect the what? The metal, right? Like this, metal connection, right? Like this, right? So this might be a very large area, consume large area and parasitic. But nowadays it might be okay. Getting better situation because the sub-micron CMOS and even now nanometer design, the width of the poly can be very small, right? The width and length here, length. So R is proportional to what? The L length over width, right? If you make it width small and small, compared to L, you can get the large resistor, right? But what would be the limiting factor for the width? The width must be poly width. You have to consider the desired level. Desired poly width must be determined by the desired level. The R. So W for the desired R. So design the W for the desired R, right? poly width and so let's say 4 desired R. The second thing that you have to consider the electron migration, meaning the maximum width, the width must be roughly larger than the, let's say, if the too much current flows through this poly resistor, then the poly resistor will burn out, so it will be disconnected. So the maximum current is like 1 milliamp per 1 micrometer width, right? So you have to double check always with your technology file. So PDK always provide the right number for the maximum amount of current. This is just rule of thumb, so just 1 milliamp per 1 micrometer. So if you or circuit or resistor have to flow large amount of current, then you have to make it very large W, or you may have to make it parallel connection of the poly, right, to make it larger, effective larger width. For example, like this, so you have to make a poly resistor in parallel, right, and then connect the top connection and bottom connection, and then like this, right? So the effective W width can be very large, right? So typically the metal electron migration and poly migration is similar. So you have to make it like a large the large metal width as well, for example. Okay. This is the rule of thumb. So this poly width rule of thumb, this is also applied to metal. Also applied to metal, right? So electron migration is a thing that you have to consider when you determine the metal width, and also you have to consider what is the resistor value you want to make or you want to target, right? In the previous example, the resistor implementation is loaded by the output, so its output impedance Rout will be decontaminated, it will be reduced. So in order to disconnect the impact of the output sensing resistor, we used like a source follower in this example. So the output is capacitive, right? The R is infinity. So we have the R out from the amplifier. Now we have the VGS drop between gate and source. The output is always VGS drop, and then sense register there. So the output common in this, the good thing is that the CMFB doesn't affect the DC gain of the main amp. But the negative point is that output common mode level sensed the CM output. CM is the real CM, VOCM minus VTH plus overdrive voltage, right? So this is VGS drop, right? Out of M7 and M7 or M8, right? So real VGS, real outcome mode is not sensed because the VTH vary according to what? To the process and temperature variation. Right? And also what we have, the body effect, right? Etc. Right? So this kind of adding follower. So follower is not well used because we cannot sense the exact level of the output cone mode. This is not popular. So I'm gonna draw what? So the first thing is good. Let's say make a smiley face. And second one is bad. Right? Another sensing scheme which is not popular is that it's using the triode region transistor here. So if for the given common mode level, so this transistor will be into the triode region. So if you flow some current through that you will get some voltage, right? So make sure that we make that this level to be some desired value, right? So make the loop construct. For this kind of a thing, the problem is the threshold voltage is there. So if the large swing occur like this, and one side is here and the other one is like this. Let's say for example V out goes up, V out 1 goes down, then it may M7 turn off, right? If that the swing is too large, right? If the V out 1 lowest peak is below the threshold voltage, then the M7 will turn off. So this is a kind of a limited output swing range, right? Output swing. And also the sensitive to PVT variation. See the on resistance of the triode, right? That's the PVT. So there should be some kind of a replica circuit to track the such variation. Require replica. So it requires some complicated replica. So I would not. So people, this is also not popular. Okay. Another technique is using the common mode sensing here. So we apply the reference, the voltage and out 1 and out 2. If the common modes are the same, if the out 2 common modes are the same as the VB, then this current will equally balanced, right? Equally balanced. The I0, let's say I0 over 2, I0 over 2, right? I0 over 2. See, one side goes up and the other side go down by the same amount. The M1 current increase, but M3 current goes down. But the overall, and then let's say this is, let's say plus delta and then minus delta, right? the M4 will be, if the VL2 goes down, then M2 will be minus delta current, and then M4 will be plus delta current. So overall current through that would be what? Same, equal, because we have a minus delta and positive delta here, that then ICM2 will be same as the what, I0, right? So it doesn't change. The output voltage VSG doesn't change. But if the out 1 and 2 goes up by the same amount, then the older the M1 and 3 will goes up, and M2 and 4 current will go down. So the output level of the diode connected PMOS will go up. So it kind of it just react to the input current mode level. But the problem is this is a differential amplifier structure, and you know that the linearity of the differential amplifier is limited, right? The maximum range is what? Square root 2 times V overdrive, right? And minus square root 2 V overdrive. So it has limited range of the operation for this amplifier. So this CMOS sensing just only effective for small output signal level, but for large swing level it might not good enough. Okay. This is cascode single-ended output. For this kind of circuit, as you see here, we have the current source and current source one here and there. But the other side is what? This is high swing cascode. This is the one the diode connected, right? The load, and on the left hand side also. So this impedance looking into diode connected load is low compared to output impedance of the transistor RO. So in that case, this node voltage is well defined, right? Even though, so whatever the current flow, let's say for example ISS or IS bottom tail current will split equally by the M1 and M2. Why? Because we have the same gate voltage and same device size, so same 1 over GM impedance, right? So it will flow through M1 and M2 equally. So once the current flows through this diode, the voltage will be always well defined by the current times impedance. So it doesn't vary a lot, right? But for the output level here, since this current level and up and down will have some kind of uncertainty, right? It has a very large output swing level, right? So this output level may go up and down to near VDD or ground. Is that gonna be a problem? Actually, not, because this kind of amplifier is always used in what? Negative feedback structure, right? So used in negative. So the output level will be well defined. The voltage is defined by negative feedback. There is some other thing, another level of the negative feedback is used. Once this kind of amplifier is used, it is always used in the negative feedback. So there is no additional CMFB is required, right? This feedback will find its value at the output, because the current mode level of the output is just signal, right? The signal is inside the negative feedback. So we don't have to sense the output in the single-ended output level, right? So whenever you have this kind of diode connected level, connected circuit there, so single-ended output amplifier, you don't need CMFB. But as you saw in the previous examples, for the fully differential amplifier, you must have additional common feedback circuits to make sure your amplifier operate at inside the desired operating point. Okay. So here we will recapture the concept of amplifier scaling. It is very important. So as you might know, so any amplifier can be modeled like a big GM. So input and big GM of the, let's say, we have the input, V in, and the current source, and the output impedance are out, right? And the big GM. So this is a typical amplifier, equivalent amplifier model, right? So you get the output, right? Voltage. Go out, right? This is ground. Let's say, for example, this kind of amplifier is here. Now, if you scale up by n times, for example, if you make it in parallel, like a parallel connection, connect the input and an output by n times, then you would get the n times larger power, because each amplifier current is n times, becomes n times. And each amplifier current is I0, then total current will be the n times I0, right? Now what about the input reference noise voltage? Input reference noise voltage case, for example, we have that each amplifier has the input reference voltage source Vn square like this. If you cascade everything, cascade n times each amplifier, the input reference noise voltage, for example, for simplicity, we will consider the input reference voltage only, right? So if you add up all the noise sources, right, then how large the noise? The noise would be, right? Is that gonna be large? If you add that up, is the noise gonna be going up? So if you look at this Vn square over 2, typically it will be the noise will be what? So noise would be 4kT, the gamma over Gm, right? For example, if the amplifier is well designed, it will be like this. If you scale up, the overall total GM will be what? N times larger, right? So equivalent noise will be, right, n times smaller, right? Noise power, it would be n times smaller. Okay. So if you convert that into RMS, the Vn RMS would be what? Root n times smaller than original RMS level. So RMS n times larger, let's say. This is how we V n time prime, let's say prime, make it prime. So larger, this is the larger, n times larger input voltage, input reference noise voltage in RMS would be n times smaller, right? So this is how so this is important to understand when you need the amplifier scaling, right? So you would scale amplifier. First reason, if you want to reduce the noise level, you scale up. The second is that when you have a given load capacitance, here the output bandwidth will be determined by what? 1 over R out CL, right? In frequency 2 pi, 1 over 2 pi R out CL. If you want to increase the bandwidth, then you have to reduce the R out. In that case, you scale up. So to increase bandwidth increased by R, so R out must be go down. So R out will go down, mean bandwidth goes up. So this is by scaling. Okay. For the given CL, right? If the CL is given, if you want to have a higher bandwidth, you may scale up. Okay. So this is the how you get the output, how you scale when you this is the case when you scale the amplifier. Okay. There's also another things. Three might be sometimes the input offset. The mismatch is the offset is the offset happened by the VTH mismatch, right? So VTH mismatch is reduced by, this is proportional to what? Square root times L area of the amplifier. So if you make it large size, then it becomes also smaller offset. Input offset goes down by the scale. Okay. This is the last thing that you may consider. Okay. Let's think about more in detail about the amplifier noise. Let's say we have a VN scare, same amplifier noise level. Scare. Let's say we add it together. What happened? So in this case, so to find out the input reference noise level of the two 2x scaled amplifier equivalent. So as we have derived in the earlier discussion, we short the output and find the output level. So this is, let's say, GM, big GM is there. So output noise will be what? Here we Vn times big GM, right? So overall I out scare N would be GM and scare Vn scare plus GM scared Vn scare. So total I out is 2x larger VGM scare Vn scare, right? So we have to refer to that input by equivalent GM. So GM is 2GM, right? So if you refer that, then what? So that would be so the referred input referred the GM. So this is big GM. So Vn equivalent scare is what? 2GM scare times the 2GM scare Vn scare. So what you get is look the 2GM scare Vn scare, right? So as I have shown in this example, input equivalent noise is power is reduced by square root what? reduced by half, right? This is reduced by half. In RMS voltage level, it is reduced by square root of 2. So as you can see, this input reference noise is not same as what? Vn square plus Vn square like this, right? This is not, right? So this is something that you have to wait a second. So 2, right? So over 2. So this is something that you have to consider. So scaling up amplifier reduce the input reference noise. Okay, so you hope you understand better for this kind of things. Okay, thank you. Now we will talk about the two-stage operational amplifiers. Now we need to begin consider the frequency compensation. This is a very important concept, but for now we will neglect the frequency compensation, even though those two-stage amplifier require the frequency compensation. But, okay. Typical two-stage amplifier construction is shown in here. The first stage, why we have more than one stage? Because we want to have higher gain. Why? Feedback loop, strength of the feedback loop is determined by the loop gain. If the loop gain A beta, we want to increase by the A, larger amplifier gain, right? The loop gain in a typical negative feedback. So we cascade two stages. The first stage typically support the high gain, and second stage support the high swing level. Although, so we more focus on the output swing level on the second stage, and first stage is high gain because the internal swing will be small because the final output will be developed at the output, right? So for example, here in the first stage, just common the differential amplifier with current active load like that, and then we have an additional source follower as an additional the common source amplifier, right? CS stage there to get the large amplification range. What is the output range? Output range minimum would be what? V overdrive of the M8 and 7. And then maximum is VDD minus overdrive of the 6 and 5, right? So this is a very large range. The first stage amplifier can be used by the telescopic, right? Because it has a cascade amplifier. Larger gain and even larger gain, and then additional gain by source follower. So this kind of amplifier structure having maximum VDD minus V overdrive and minimum overdrive is called the rail to rail swing. What is rail? Rail means supply and ground, right? So it can up to near VDD and near ground swing can be supported by this kind of output structure. Okay. In the previous example, fully differential amplifier was used. For that case, typically CMFB is required. And for this single-ended output, we have a diode connected load, so that the final stage we have like this, so enough large swing range, the swing and no CMFB, because this is single-ended output, right? But the frequency compensation is a different story. But that's so compensation is required. But for this section, we will neglect that frequency compensation.